A raindrop is born about 2 kilometers above your head, sometimes higher, sometimes 4 kilometers up, which is roughly the height of 7 Empire State Buildings stacked on top of each other. And the moment that drop lets go of the cloud, gravity grabs it, pulls it straight down, accelerating it the entire way. Now, you learn this in your first week of physics. It is the simplest calculation in the book. Something falls from a height, and you want to know how fast it is going when it arrives. You take the height, multiply by twice the acceleration of gravity, and take the square root. That is it. Any student can do it. So let us do it. A raindrop falls from 2,000 meters. Plug in the numbers. What do you get? About 200 meters per second. That is roughly 450 miles per hour. And if the cloud is a bit higher, say 4,000 meters, the number gets worse. 280 meters per second, over 600 miles per hour. Now stop and think about that for a moment. A 9mm bullet leaves the barrel of a handgun at about 400 meters per second. So a raindrop falling from an ordinary rain cloud in a vacuum would arrive at your head traveling at roughly half to two-thirds the speed of a bullet. And it is not alone. In a decent thunderstorm, something like 100,000 drops can hit a single square meter of ground every second. 100,000 tiny projectiles, each traveling at hundreds of meters per second, landing on your shoulders, your face, your scalp. That is a machine gun. That is not weather. That is warfare. And yet, last Tuesday you probably walked through rain, and the worst that happened to you was your shoes got wet. So either the calculation is wrong, or something very interesting is going on. And I will tell you right now, the calculation is not wrong. Not a single number in it is wrong. Every digit is correct. 200 meters per second from 2,000 meters. Verified. Confirmed. Basic Newtonian mechanics. So why are you still alive? Well, the answer that most people will give you immediately is air resistance. And they are right. They are absolutely right. But saying air resistance is like saying the doctor fixed it. Okay, but how? What actually happens between the cloud and your forehead that turns a lethal projectile into a mild annoyance? Because the drop does not just slow down a little. It slows down by a factor of 20. It goes from 200 meters per second to about 9 or 10 meters per second. That is roughly 20 miles per hour. That is the speed of a bicycle. Somehow the atmosphere takes an object traveling at the speed of a bullet and gently delivers it to your face at the speed of a kid on a bicycle. That is an enormous thing to accomplish, and if you do not find that extraordinary, you are not paying attention. Let me walk you through what actually happens to that raindrop on the way down, because the story is much richer than people think. The drop forms in the cloud. It starts from rest. Gravity pulls it. For the first fraction of a second, the drop accelerates freely, just like any falling object. 9.8 meters per second squared. Galileo's number. Nothing unusual. But immediately, the instant it begins to move, air starts to push back. Not much at first. At low speeds, air resistance is tiny. You do not feel air resistance walking across a room. But here is the critical thing about drag. The force that air exerts on a moving object. It does not increase in proportion to speed. It increases in proportion to the square of speed. Double your speed, quadruple the resistance. Triple your speed, 9 times the resistance. This is not a gentle, linear thing. This is an escalation. And it escalates fast. So the raindrop speeds up and the air pushes back harder. The drop speeds up more and the air pushes back much harder. It is like running through a crowd. At walking speed, you slip between people easily. At a full sprint, you are slamming into shoulders and elbows. At the speed of a car, the crowd becomes a wall. That is what air does to a raindrop. The faster the drop moves, the more violently the air molecules slam against its front surface. And because drag scales with the square of speed, the resistance ramps up ferociously. Within a few seconds, and within just a few meters of fall, something remarkable happens. The drag force climbing upward meets the gravitational force pulling downward, and the two forces become exactly equal. At that instant, the net force on the drop is 0. And when the net force is 0, the acceleration is 0. The drop stops speeding up. It has reached what we call terminal velocity. For a typical raindrop about 2 millimeters across, this terminal velocity is roughly 9 meters per second. For a larger drop, maybe 6 millimeters in diameter, it is closer to 10. That is the ceiling. That is as fast as it will ever go, no matter how far it falls. You can drop it from 2 kilometers or 10 kilometers or 100 kilometers. The number does not change. Once it hits terminal velocity, that is it. The atmosphere has spoken. And here is the part I find truly beautiful. The drop reaches terminal velocity very quickly, within a few dozen meters of fall. After that, it is just coasting, drifting, falling at a constant speed through kilometers of air. A raindrop that starts 4,000 meters up reaches its terminal velocity within about the first 100 meters, maybe less. The remaining 3,900 meters, a long quiet ride at 20 miles per hour. Think about what that means. 97% of the journey is at terminal velocity. The dangerous part, the part where the drop is accelerating like a bullet, lasts less than a second. It is over almost before it begins. The atmosphere intervenes that fast. But you should ask a deeper question. Why is the terminal velocity of a raindrop so pathetically low? After all, a skydiver, a human body, reaches a terminal velocity of about 55 meters per second. That is more than 5 times faster than a raindrop. A bowling ball would be even faster. Why does the raindrop max out at such a tiny speed? The answer is about shape and size and density, and the relationship between them is not what you might guess. See, gravitational force depends on mass, which depends on volume. For a sphere, volume goes as the cube of the radius. But drag force depends on the cross-sectional area, which goes as the square of the radius. So as the drop gets smaller, the gravitational pull shrinks faster than the drag does. The ratio shifts. For a tiny drop, drag dominates gravity almost immediately. A small raindrop is practically all surface and very little mass. Think of it this way. Imagine you have a cannonball and a ping-pong ball. Drop them both from a tower. The cannonball plows through the air because it has tremendous mass for its size. The air can barely slow it down. The ping-pong ball, same shape, same drag coefficient, but almost no mass. The air stops it immediately. A raindrop is much closer to a ping-pong ball than to a cannonball. It is a tiny sphere of water with a mass of about 1/20th of a gram. The air barely has to try. And that is only half the story, because raindrops are not even stable at large sizes. In the cloud, drops form small and grow by collision and coalescence. They bump into each other. They merge, they get bigger. But there is a limit. Once a drop gets above about 5 or 6 millimeters in diameter, it becomes unstable. The air pressure on its underside as it falls flattens it, stretches it. The drop goes from a sphere to something like a hamburger bun shape. And then it breaks apart, it shatters into smaller drops, each of which has an even lower terminal velocity. So the atmosphere has 2 defenses. First, drag slows the drop down. Second, aerodynamic forces prevent the drop from getting big enough to carry serious kinetic energy. Nature has built a ceiling and a wall. You cannot go faster than terminal velocity, and you cannot get big enough to make terminal velocity dangerous. Let me give you the energy numbers, because the speed comparison alone can be misleading. People hear 200 meters per second and think of a bullet, and they imagine a bullet's damage. But speed is only half of kinetic energy, the other half is mass, and here the comparison falls apart completely. A 9mm bullet has a mass of about 8 grams. A raindrop has a mass of about 1/50th of a gram. That is a factor of 400. So even if the raindrop were traveling at the same speed as the bullet, it would carry only 1/400th of the energy. The kinetic energy of a 9mm bullet is about 600 joules. The kinetic energy of a raindrop falling freely in a vacuum from 2,000 meters would be roughly 2/3 of a joule, less than 1. And the kinetic energy of an actual raindrop at terminal velocity is about 1/1000th of a joule. You would need about 600,000 raindrops hitting you simultaneously to deliver the energy of one bullet. The atmosphere does not merely reduce the danger, it obliterates it. But I want you to think about something else. I want you to flip the question around. Instead of asking why rain is harmless, ask what it would mean if it were not. Imagine there were no atmosphere, not just no air resistance, I mean no air at all. The drops would fall freely, accelerating all the way, and each one would hit the ground at 200 meters per second. What would that look like? It would look like being sandblasted. The surface of the earth would be scoured. Standing water would be impossible, because the incoming drops would blast apart any pool, any puddle, any lake. Soil would be stripped bare in minutes. Trees, if they could even exist, would be shredded. Leaf tissue is soft. At 200 meters per second, a water droplet punches through soft material like a tiny fist, and any animal caught outside would be hammered by millions of tiny impacts per second, each carrying enough momentum to sting, to bruise, to erode skin over time. It would not be an instantly lethal rain the way a bullet is lethal, because each drop is still very light, but it would be a relentless grinding assault. Think about how a water jet cutter works. It is just water, but at high enough speed it slices through steel. The drops would not be that extreme, but the principle is the same. Speed transforms water from gentle to destructive, from something children play in to something that reshapes stone. There is an old physics intuition that Feynman himself used to illustrate a point about the impulse of many small things. He talked about running in the rain, and how the rain hits your face harder when you run into it. More drops per second from a steeper angle. That is basic momentum transfer. Each drop carries a small impulse, mass times velocity, and the total force is the sum of all those impulses per unit time. At 20 miles per hour, the impulse per drop is tiny. At 450 miles per hour, it would be something you could feel. Multiply by 100,000 drops per second per square meter, and you would absolutely feel it. It would hurt. So the atmosphere is not just slowing things down. It is transforming the entire character of an event. It is taking what would be a violent, destructive bombardment and converting it into something soft enough that children play in it, something gentle enough that poets write about it. The same water, the same gravity, the same height. The only difference is a blanket of gas. And this, I think, is what makes physics so endlessly interesting. The obvious things are never as simple as they seem. Oh, you walk through rain your whole life and never once think about the fact that the air above you is performing a continuous invisible act of protection. Every second of every rainstorm, the atmosphere is absorbing the vast majority of the kinetic energy that gravity tried to give those drops. Where does that energy go? It goes into heat. The drag force heats the air and the drop microscopically by the tiniest amount, but the total energy dissipated across an entire rainstorm is enormous. That heat eventually radiates away, becomes part of the great thermal circulation of the atmosphere. The very system that makes rain also makes the rain safe. There is a kind of elegance to that. The atmosphere creates the conditions for rain to form, lifts the water up, lets it condense, lets it fall, and then catches it on the way down. It is a self-regulating system, not designed, not planned, just the inevitable consequence of the laws of physics operating on a planet with water and air and sunlight. Now, some people hear this and say, well, but I already knew about air resistance. Everyone knows about air resistance. And that is true. You did know. But did you know the numbers? Did you know that without air, every rainstorm would be a catastrophe? Did you know that the drop reaches terminal velocity within the first 100 meters and coasts for the remaining 3,900? Did you know that the energy ratio between a raindrop and a bullet is 600,000 to 1? Because that is what physics does. It takes something you think you understand and shows you the thing you had not noticed. You knew the answer, air resistance, but you did not know the size of the answer. And in physics, the size of things matters. Knowing the direction is not enough. You have to know the magnitude. And when you know the magnitude, the familiar becomes astonishing. Let me give you one more thing to think about before I finish. That Mars has an atmosphere. A thin one, only about 1% the density of Earth's atmosphere. If it rained on Mars, which it does not currently, but suppose it did, the raindrops would still experience some drag. But 1% the density means drastically less drag. Terminal velocity on Mars would be vastly higher. A raindrop on Mars would hit the ground at something like 10 times the speed it does on Earth. Maybe 50 or 60 meters per second. Still not a bullet, but not a gentle shower either. It would sting. It might leave marks. You would need shelter. You would need armor. Rain on Mars would be an event, not an inconvenience. And on a world with no atmosphere at all, like the moon, water released from a height would hit the surface at full vacuum speed, 200 meters per second from 2 kilometers. A stream of projectiles. Every rain event would be erosion. Every shower would sculpt the landscape like a chisel. So the next time you are standing in the rain getting annoyed that you forgot your umbrella, I want you to remember this. Every drop that touches your skin has been traveling for 7 minutes. It fell from 2 or 3 or 4 kilometers up. It started accelerating toward you like a bullet. And then the air you breathe without thinking, reached out and grabbed it, slowed it by a factor of 20, stripped away 99.9% of its kinetic energy, and delivered it to your cheek at the speed of a bicycle. You are being protected right now by physics, by the simple fact that drag force scales with the square of velocity, and that water drops are small and light. That is all it takes. Two facts, and those two facts are the difference between a gentle afternoon rain and a planetary scale sandblaster. Tell me, what other everyday thing do you walk through without realizing how violent it almost was?